Good morning. I'm Ramakrishnan from the Indian Institute of Science. I'm going to talk about optimal algorithms for range searching over multi-arm bandits. This is a joint work with Siddharth Barman and Rahul Saladi. Multi-arm bandits is a well-known framework in online optimization and reinforcement learning, which has been extensively studied in the last few decades. Say we have three drugs, A, B, and C, that can treat a disease, and we would like to find out which is the best among these three. But the true efficiency of a drug is not known upfront. This can be estimated only by testing it on some people. Then, what would a smart testing strategy be? How do you ensure a bad drug isn't tested on people very often? All these questions can be well answered by modeling this problem in a multi-arm bandits framework. It gets its name from the bandit machine that you see in casinos, where when you pull its arm, you get a seemingly random prize. MAB has a lot of practical applications. For example, in online advertisement, you want to show ads to a user, but you don't know upfront the attractiveness of different ads that you have in hand. Here, we need a smart way to try out different ads to maximize the number of user clicks. Another example could be in crowdsourcing, where there are many workers whose efficiencies are stochastic quantities not known a priori, and we might want to find out the best worker as early as possible or by adhering to some budget constraints. Now, on a seemingly completely unrelated note, range searching is a very fundamental and basic area of research in computational geometry and databases. The general problem paradigm is you have a set of points in a search space and each point has a weight associated with it. And you're given a bunch of queries asking for maximum weight point or count of points, etc. within the queried space. One particular problem in this family is the one-dimensional range searching problem. You have points on the real line, which is the search space here. Each point has a weight associated with it. Then you have a bunch of input query intervals, and the objective is to find within each queried interval the point with maximum weight. For this example, these 3 points are the answers, that is, the maximum weight point in their respective query intervals. This problem is very fundamental in designing database query algorithms. Another stylized example would be to find the restaurant with the highest rating in different stretches of a highway. Here, highway is comparable to the real line, and the ratings of a restaurant is its weight. Zooming out a little, both computational geometry and multi-arm bandits are classic fields on their own right. They have graduate level textbooks and a rich research literature. There are so many different problems and so many different settings in both of them. Recently, with technological advances, data has become ubiquitous and most of it is also stochastic or approximate, like the GPS locations, quality of workers, attractiveness of online advertisements, real-time measurements from IoT devices, etc. This opens up a lot of problems in the intersection of these two fields. We, in particular, look at the overlap of two specific problems, the range searching and the best time identification, drawing insights from both the worlds. Strangely, problems in the intersection of these two classical fields are relatively underexplored. In our novel setting, range searching over multi-arm bandits, for the set of points, the positions on the real line are fixed, but the weights are stochastic. They are not known deterministically. As a stylized example, in a crowdsourcing work environment, the salary is fixed and known, but the efficiency or productivity is an uncertain, it's a stochastic quantity. And we want to find the most efficient employee in different salary ranges. Note that this setting is different from some of the previously studied settings where the position along the x-axis is uncertain. Here, the position along the x-axis is fixed and known, and it is the weights along the y-axis that are stochastic. In fact, our setting generalizes both the classic range searching and the best term identification problems. If the weights are not stochastic, we get the typical range searching problem, and if all the points have the same position, we get the basic best term identification problem. Let us mildly formalize our setting. We are given a bunch of points. For each point I, its position pi on the x-axis is known, whereas its weight wi on the y-axis is not known upfront. Each point's weight is governed by an unknown random variable behind the scene. The only way to learn the weight wi is by sampling its random variable, that is, to pull that arm to get an estimate of the true weight wi. So, in our setting, all you can gather is a high probability confidence interval for the weights. That is, with the high probability, the true weight wi is somewhere within this range shown here. The more you sample, the closer the estimate is expected to get to the true weight. That is, the confidence interval about the true weight shrinks, and beyond some stage, clear distinctions between the weights begin to emerge. Here, with the intervals well separated, you know with a high probability that wj is larger than wi. We are also given the bunch of input intervals up front. Note that this is in stark contrast against the online or sequential nature of queries that we see in the classical range searching settings. Now, the goal here is to find, with high probability, for each input interval, a point with approximate maximum weight within that interval, which would be this point with the yellow box for this yellow interval. A naive way to do this would be to sample the weights or arms sufficiently many times so that, by the law of large numbers, we have accurate enough estimates for all the weights, and then it becomes easy to compute the maximum weight point. The challenge, however, is to find the required points by making as few samples as possible. For the range searching over multi-arm bandits problem discussed in the previous slide, we come up with novel optimal algorithms establishing theoretical guarantees for upper bounds of the number of samples required. Importantly, we prove the tightness of our upper bounds by establishing matching lower bounds. We also extend our algorithm to handle multidimensional weights and provide theoretical upper and lower bounds for them as well. In our work, we make interesting connections between our problem and the geometric construct that hitting sets are. For sampling the weights of points in an efficient and smart fashion, we come up with an elimination algorithm that follows the medium elimination paradigm well known in the MAB community. In the forthcoming slides, we shall see a little more about these techniques to get a feel for them. We find that the number of samples doesn't depend directly on the number of given input intervals. Instead, it depends on the size of the minimum hitting set of the input intervals. Let's take an example. A bunch of 5 intervals. A hitting set is a set of points that contains at least one point from every input interval. This point hits through intervals 1 and 3. The second point hits through 2, 3 and 4. This third point hits intervals 2 and 5. It can be seen that this hitting set is of minimum cardinality. That is, there is no other hitting set with lesser points. The size of the minimum hitting set is denoted by tau and has a value of 3 in this example. Realize that tau can be significantly smaller than the number of input intervals, which is 5 here. For another example, a bunch of intervals with a common intersection would have tau as low as 1. The points of the hitting set partition the rear line into a series of disjoint slabs. We get tau plus 1 slabs. Because we use the points of the hitting set to partition the rear line, every input interval overlaps with at least 2 slabs, which is very crucial. In a sense, we break the problem into smaller, simpler problems to be dealt with within each slab. And look at the points within that slab. We want to sample these points efficiently and create a small set of candidate points. And we use a halving technique and iterative approach for this. Without getting much into the nuances and complete details of the entire algorithm, I'll just give you a rough visual walkthrough on the intuition of the idea. We first divide the weight axis or the weight space into bands. In every iteration or round, we sample the active points a conservative limited number of times. From every band, among the points whose estimated weights fall inside it, we discard half of the points with smaller position value that is along the x-axis. We do this for all the slabs, and then at the beginning of the next iteration or round, we again sample, but only the remaining active points are sampled. This is how we make savings on the number of samples and keep it to a minimum. Finally, when the number of remaining points is below some threshold, we sample the remaining set of points sufficiently highly and calculate an approximate skyline which serves as the candidate set from this slab. In the interest of time, we skip the details of what a skyline is and why skyline is an ideal choice for the candidate set. Let us look at one input interval with these boundaries. First, we had split the real line into slabs using hitting set. Second, we obtained candidates from all the slabs. Third, to answer for this input interval, we consider only the points belonging to the candidate sets, and we pick the one with the maximum estimated weight as our answer for this interval. However, recall that we only have high probability confidence intervals of the true weights of points, because we work on the estimates. Thus, the points that we find are approximately maximum weight with a high probability. We summarize our results in this slide. We created optimal algorithms for the problem of range searching over multi-arm bandits and established upper bounds and tight lower bounds for the number of samples. In that expression, n is the number of points or arms, tau is the size of minimum hitting set of the input intervals. We also extend our work to multidimensional weights, where d is the number of dimensions. Some intuitions and details are indeed brushed under the carpet. Detailed explanations, algorithms, and proofs can be found in our paper mentioned at the bottom right. For possible future directions, I bring back an earlier slide. We worked on the amalgamation of the range searching and the multi-arm bandits problems. We believe our work initiates the exploration of a rich overlap between computational geometry and multi-arm bandits. For example, in the range searching in the regret minimization setting, the goal is to avoid sampling points with less weight too many times, while finding the max weight points for the given intervals. In the convex hull problem, the goal is to find an approximate convex hull of the points given with as few samples as possible. Nearest neighbors in dueling bandits could be a fascinating formulation, where you don't get to sample how near a point is to some reference point. Instead, you only get to sample 2 points and observe a noisy result of which of these 2 points is closer to the reference point. We really believe there can be many more interesting and non-obvious problems in this intersection of computational geometry and multi-arm bandits. Thank you so much for your time.